everybody. My plan here is we're going to talk about some test 6 stuff because we moved the test 5 date till Tuesday next week. So we're going to talk about some additional integration techniques that we can use on rational functions. So this is not specific, like one specific textbook topic. I just kind of pulled and made it, well, it simplified some of the stuff that's in the textbook to a level that is appropriate for an AP classroom. That would mimic the level of question you get on an AP exam. And then combine these topics into one place rather than spread it across different sections. So we're going to do that today. I'm going to give you guys some optimization practice to work on. So just like during test 5, in the background while we were doing stuff, we were working on related rates, which is a semester 1 topic. During test 6, in the background while we're working on those new topics, will be practicing optimization, which is, again, a semester 1 topic. So I'll give you that stuff. I'll probably be about 40 to 50 minutes doing this. And we'll look at some test 5 review stuff. Look at some AP questions or some multiple choices or free responses or whatever you guys feel like looking at. And that'll probably be our day. Sound good? Yeah. Okay. All right. So here we're going to have 3 different integration techniques we're going to look at. They're all going to be used to integrate a rational function, because as of right now, the only 2 antiderivative formulas we have that'll include any way, shape, or form a rational function is 1 over x is the natural log, that's value x, and 1 over 1 plus x squared is tan inverse x. Right? Here we're going to look at some techniques we can use to take things that don't look like either of those and make it look like it so we can do a use of with it. But that's going to be kind of the goal here. Okay? The tricky part is I'm going to give you guys, or talk about hey, this is kind of what you look for in order to decide whether you use this one or that one. But sometimes they overlap. And it's hard to tell. The situations can overlap. So the first one is the clearest situation. For the first one, we just need the degree of the numerator to be greater than or equal to the degree of the denominator. And realistically for you, that denominator degree has to be 1. I would not give you something where the degree was greater than 1. The AP will not give you something where the degree was greater than 1. Expect you to use this method on it. Everybody's cool? Okay. So the technique here is we're just going to use polynomial division. Will be the technique we use to get this into a form where we can integrate. So remember when you guys talked about polynomial division in Algebra 2 and in pre-calculus, there's 2 different techniques you can use to do polynomial division. There's long division and synthetic division, right? Which one do we prefer to be able to do? Synthetic. What conditions do we need in order to do synthetic division? Because you can't do it every time. There's 2 things that you have to have. 0. You need 0. You need a 0? Okay, sure, but what if you don't have a 0? You still should be able to do synthetic division. That's if you're going to use it to factor. You need a 0. But we're not going to, we don't need to factor. Sam?
I don't know.
Okay, so the denominator, your divisor, needs to be
1.
It needs to have a degree of 1 and a leading coefficient of 1. Okay? So it has to be just like a regular x as your leading term. You can still make it work with your leading if you have a coefficient, but it's like you have to do some extra cleanup at the end. That's not something I would expect you to do. And in all reality, at that point, it's probably easier to just do long division. So let's set this up. So you set the denominator equal to 0 and solve, and that's the number that goes on the outside. And then the coefficients from the numerator go on the inside. You have to make sure that every degree is represented. Like if you're starting at degree 4, you should have 5 numbers. If a term is skipped, what do you have to do? Put a 0 there. You guys remember that? Okay. How do we start?
Bring the 1 down.
Bring down the 1 to start, and then multiply, and then put it in the next spot, and then we add down, and then repeat until we're filled, right? Does that ring a bell? Now those numbers underneath those bottom 4 numbers mean something. How do I interpret those bottom 4 numbers?
This was the x squared,
Yeah, usually I like starting from the right. So the furthest number to the right is the remainder, and then the constant, the x coefficient, and the x squared coefficient. So from this here, we can say that x cubed plus 7x squared minus 3x plus 5 over x plus 4 is the same thing as x squared plus 3x minus 15 plus the remainder over the divisor. Does that all ring a bell? Look familiar? Should have done this in pre-calculus and algebra 2, really. We do it in both places. So remember, we want to talk about integration technique here, or being able to integrate these things. So if I wanted to integrate that function, the way it's currently written, nothing to do. Like I have no integration or antiderivative formula to handle that. It's a big old mess. But if I do that division, that polynomial division that we just looked at, and instead think about integrating the function when it looks like that now I can handle. So we can integrate this piece by piece. What's the integral of x squared? Okay. And the integral of 3x? The integral of 15? Okay. And then for this last piece, what am I going to do on this last piece? I can still integrate that, I just need to use a u substitution, right? What should my u be? X plus 4. Which means when I differentiate both sides, the du is just going to be dx, right? So I can pull the 65 out front, and we're going to be integrating 1 over u du. I'll pause here and let you guys think that through and make sure you see it. And the substitutions that I made. What is the integral of 1 over u du? Yeah. So natural log, absolute value, and then I'm going to put the x's back in for the u. And there's my answer. Might be able to clean that up a little bit, but I wouldn't worry about it too much. That's pretty good. Does everybody feel okay with what we did on this one? Ava?
What was the trick for like when you're taking the antiderivative for something to the power of something? Like you said there was a trick last time.
You're just talking about like this?
Yeah, but like there was, I don't know, like there's something simpler.
You flip the numerator to the
Oh.
fraction.
Oh, yeah, if it's a fractional denominator,
Okay.
but none of our denominators are fractions, they're just whole numbers, so there was nothing
Okay.
goofy to do there, right? So just plus 1 to the exponent divided by the new exponent. And since the exponent's a whole number, no worries. Is that okay?
Yeah.
Perfect. Okay. This is the easiest one. The easiest of the tricks is to just be able to do the division. It's the easiest one to recognize. The last two techniques are harder to tell apart when to do which. So this one, typically you're going to see a degree 0 over some trinomial that's in the quadratic form, and I guess I should say, let's see that. So examples of other polynomials that are quadratic, that could be in the quadratic form, like x to the fourth plus something x squared plus a constant, or x to the sixth plus something x cubed plus a constant. You guys get the pattern, right? Where the degree is 2n, n, and then degree 0 over your three terms. So in this case, the trick is going to be using completing the square. Because the goal here is I want to make it look like that, so I can use the tan inverse antiderivative. Okay? That's my goal. This is the antiderivative formula I need to use to do this. So somehow I need to take this and rewrite it as like 1 plus something squared. Is okay? So when I'm completing the square, the steps to review this is, again, something you would have done in Algebra 2 and probably in pre-calculus again. What's the first step? What is the first thing I have to have? The leading coefficient has to be 1. If it's not, I'll factor, take a greatest common factor, or I'll factor so that it is 1, right? Even if it means making fractions, that's fine. Okay. What do I do next? We'll add and then subtract b over 2 squared. So here the leading coefficient was already 1. What is the b on this? 4. So I'm just going to go ahead and subtract b over 2 squared. Notice because I'm adding and then just subtracting, what am I doing? Nothing, right? I just added 0 to this, so it still is the same value. I've just written it in a different way. Everybody agree? And then our final step is to regroup and factor the perfect square. So those guys are going to be part of my perfect square. And then which other term is the third piece that I need? Because it's plus, I need the plus b over 2 squared. Everybody okay there? So I know by the way that completing the square works, when I factor x squared plus bx plus b over 2 squared, that's just going to give me my factored form, right? You guys look really unsure of what I've just done. Can you give me some feedback and I can try to clear up whatever's ailing you? Sam.
So like for completing the square, just go over time.
Yeah, so there's basically 3 steps. First step is we need to make the leading coefficient 1. In this problem, it was already 1. I didn't have to do anything there. The second step is to add and subtract b over 2 squared. So my b was 4, so I added 4 over 2 squared and subtracted 4 over 2 squared. The third step is to regroup and factor the perfect square. So the group that I need to make is going to be x squared plus bx or minus, depending on what the bx term is, positive or negative, and then the b over 2 squared. So that's what I took there. That's the group that I'm going to be factoring. The other pieces are just the leftovers on the outside. Everybody okay there? This perfect square will always factor to just be x plus b over 2, or minus, depending on if the bx term is positive or negative, and then squared. So that's what I got there. And then 5 minus 2 squared is 5 minus 4, which is just plus 1. Sam, does that feel okay? That help just doing it one more time? Okay. So reminder of where we were at. We had this. Nothing we could do here. No integration formula will cover that. We'll perform completing the square. That's going to get me to here. Now I can do a u substitution. So the u I'm going to pick is the x plus 2. So du is just going to be dx. And what is the antiderivative of 1 over u squared plus 1? Tan inverse. And we'll just plug our u back in, which was x plus 2, and we're done. Yeah, and
Useful.
yep.
At the beginning, since you need 1 plus x squared, could you just subtract? Like, say it did make a perfect square, you just subtracted 1 from 5. Could you make it 1 plus whatever polynomial is there?
You just want to think about it that way and jump straight to it.
That feels easier.
It does, assuming that the 1 is what you're going to get left over, which it might not be. This one is the easiest version of this problem where the leftover was a 1. If the leftover was like a 9, then we have to factor out a 9 from the denominator. So like, just as a hypothetical, let me pick a... So let's say we had this. Right? There's no reason that leftover has to be a 1. So what I would do is I would take a greatest common factor of 9 out of the denominator, because I need this to be a 1. So when I factor a 9 out of this, what does that become? Well, I'm going to put the 1/9 out front, but over 9 would be fine also. Okay with that? Now I don't want this here because when I do my U sub, that's going to be a problem, right? So I'm going to think about that 1/9 as like 1/3 squared. And because these are both squared, guess what I can do? I can like push that 1/3 inside, right? And now I'm at a spot where I can build my integral and go. So you should not assume that I just strip a 1 off and then whatever's left is going to make my perfect square. That doesn't have to happen that way. That's the easiest version. That's the most likely thing you can see on an AP exam because, like that what we just did is kind of a mess. Much harder because of the factoring stuff that has to happen at the end and figuring out, I can push the 1/3 through there and put it back in. And, if this was not a perfect square, then you have if this was like a 7 or something, you'd have like 1 over the square root of 7 squared, and you get like radicals and stuff popping around it, and it becomes kind of a hassle. But there's nothing to say it can't be a hassle.
Should we expect something like that on the test?
Well, we're talking about test 6 stuff. I haven't even.
Of course.
So you're like a month away from now. So I don't know the answer to that. Probably not. But you can see why now that you have to be a little bit careful. Don't assume too much when you start doing this completing the square thing, right? Yes.
How can you tell the difference between where you need to do polynomial division and where you need to do completing the square?
Okay. So if the degree of the numerator is greater than or equal to the degree of the denominator, it must be polynomial division.
Mm-hmm.
If it's not, then it's either going to be this tan inverse completing the square piece, or going to be the next option.
Okay.
We'll look at the next option here in a moment. Okay? Is everybody okay with how we finish this guy up, though? And Anthony, you're good with my counterexample to you, why we do have to be careful about the completing the square piece, why we can't just jump straight to assuming there's a 1 left over. It'd be nice if that was the case every time, because that's the easiest version of this kind of problem, and there's a 1 left over. Okay. Last type. So here again, the degree of the numerator is less than the degree of the denominator, but the denominator this time is going to be factorable. Notice that this denominator, not factorable. That's how we know it's a tan inverse problem. This denominator is factorable. We're going to do something different here. Okay? So the technique for this one is a partial fraction decomposition. That's what PFD stands for, partial fraction decomposition. So let's show you guys how to do this. And again, this is a topic that I could treat as like a standalone. This could get the partial fraction decomposition by itself without the integration. Could be a whole day to cover all the different cases and how to deal with it. I don't want to do it that way. I'm going to just do it to the level that we would expect you to do it rather than the most general level where we have a million different, like, oh, what if this happens? Or what if that happens? We're just going to do it simply. So by that I mean I won't have any repeated factors in the denominator. So to do a partial fraction decomposition, the first thing I do is factor the denominator. And that should be easy. That's like a 1 second process, right? Should be very, very good at factoring quadratics. What I want to do now is I know that this single fraction was this result of something over x plus 2 plus something else over x plus 3. Everybody okay with that? That I had these two separate fractions that I would made a common denominator and added them together and gotten that. If I had 3 factors in the denominator, 3 unique factors, I'd have 3 separate fractions that I would have to add together, right? If one of the factors repeats, it'd be a little different. We're not going to cover that situation though, so don't ask me about it. Or if one of the factors was nonlinear, like it was a quadratic term or something, a little bit different, we're not going to cover that. Just letting you know. For those of you that are at some point future engineers, you will go through and do all this partial fraction stuff at some point, or maybe somebody will just expect you know it, and you have to go back and figure out what to do in those situations. But I'm not going to cover it right now because it turns this into a 20-minute explanation into like a 60-minute explanation. I'm just going to conserve some time here. Okay? I'd love to do everything like into excruciating details I would like, but there's only so much time we have together. So I'm going to treat this as an equation. I want to solve this equation for A and B. I want to find out what those values had to be. Everybody good? To solve that equation, the first thing I'd want to do is get rid of the fractions. What would I multiply both sides of that equation by to get rid of the fractions? X plus 2 times x plus 3. So when I do that, I'd have x plus 1 equals a times x plus 3 plus b times x plus 2. Everybody feel good as to how I reduced and simplified down to there? You guys see it? Next thing I'm going to do is just distribute things through. Everybody good to this point? So now, if I'm combining like terms, I add ax and I add bx, they have to give me 1x. Everybody see that? So I know then the coefficients, a plus b has to equal 1. Feel pretty clear to you guys? And I could say the same thing then about the constant terms. That 3a plus 2b has to give me the constant 1. Does that feel okay? What have I just created? A system of two equations, right? That we can solve now for A and B. What's going to be Mr. Kulik's preferred method of solving this system? Elimination, valid, but not what I would use. Substitution, valid, not what I would use. What?
Multiplication.
No. What else could we do? Graphic. Could do it, not what I would use. What if it was 3 variables? I would have instead of just A and B, what if I had 3 equations and 3 variables? Or 4 equations and 4 variables? Oh, yuck. This is getting pretty bad. What am I going to use? I'm going to use a matrix and solve this on my calculator. Okay? Let's review how to do that. All the methods you described, substitution, elimination, graphing, all perfectly valid. Yes, you could do all of those. And as a 2-variable system with nice, neat coefficients like this, probably not much faster to use the matrix than it would be to just plow through it by hand using one of those methods. They're all perfectly valid. But if this is a 3-variable system, or a 4-variable system, or God help us, like a 5-variable system, I want no part of doing this by hand, right? Okay. So, the first thing I want to do is make sure that my system is properly formatted so that I can enter it into a matrix. For it to be properly formatted, my variables have to line up vertically. So A's are on top of A's, B's are on top of B's, equals on top of equals, solution is on top of solution. Everybody's okay? The system is properly formatted. I wrote it this way because I knew what I was going to want to do before. So to enter this into a matrix, I'm going to press second, and then the matrix button on my calculator. To enter data into a matrix, I'm going to go over to the Edit tab. Now, the first thing I have to do is tell the calculator the dimension of my matrix. So dimension is always number of rows, that's left and right, by the number of columns, that's up and down. So I have 2 equations, so it's a 2 rows, and I have 3 columns. I have a column for A's, a column for B's, and a column for the solution. Everybody feel good? So to enter the data into my calculator now, I'm just going to take the coefficients from each row. So 1A, so just 1. 1B, so just 1, equals 1. And then I have 3A, two B equals 1. Is everybody cool with how I entered the system into a matrix? Made the translation between the two. Very easy, right? You guys done this before? Okay. I'm going to exit out now. The command I need is called RREF. To find that command, we'll go back to the matrix menu. And this time we'll go over to the Math tab. And the command I want, I think, is B. So I'm going to scroll down. There it is. Make sure you pick RREF. For those of you that are curious, that stands for Row Reduced Echelon Form. It's basically an algorithm programmed into your calculator that kind of does the same thing as elimination. It's kind of what you're doing there. It's pretty similar procedurally. And I'm going to do that on my matrix A. So I'll go back to the matrix menu, and from the Names tab, I'll select matrix A, close my parenthesis, and press enter. So this output, this matrix, tells me my answer. If I read each row is an equation. So the first row says 1a plus 0b is equal to negative 1. So a is negative 1. The second row says 0a plus 1b is equal to 2. So b is equal to 2. Is everybody okay? So what we've done then is said that this matrix, or this rational function, is equal to negative 1 over x plus 2 plus 2 over x plus 3. Everybody good there? That's going to be the key that I want to make this integral possible for us. So again, starting spot, nothing for me to do. To do my partial fraction decomposition. Oh my goodness. Allows me to rewrite it. If I look at the first fraction, that's now something I can integrate using a u substitution. And the second fraction, also something I can integrate, just doing another substitution. This time I'll use the letter v since I'm using, is everybody okay there? So what I really have then is negative 1 integral 1 over u du. And then I have, oops, pressed it, 2 integral 1 over v dv. Can we see the substitutions that I've done? No.
Can you explain real quick how you went from the matrix to the two rational?
So I found my values for a and b. So I went back here, and I just plugged the negative 1 in for a,
Right.
and the 2 in for b.
From the negative 1 for A to B.
Right, because that was the solution we got out of the matrix.
Okay, I see it. Thank you. Okay, thank you.
Yeah, no problem. So the antiderivative of 1 over u is the natural log of absolute value u. Well, let's plug our x back in. And then the antiderivative of 1 over v is going to be the natural log, the absolute value of v, but let's plug our value for v back in. Is everybody okay with what I've done there? Want to hear the bad part? If it's a multiple choice question, that ain't how they're going to be. That isn't going to be one of your options. They're going to simplify this more. What simplification would be done? Properties of logarithms. So remember that these coefficients at the front of our logarithms can be moved inside the logarithm where they become exponents. And remember, to the power of negative 1 is like a reciprocal. And then the sum of two logarithms can be the product inside the logarithms. That's how they write it as a multiple choice solution. They would just condense the logarithms down into a single log. 8.
I thought when there's like division inside of a logarithm, that's like subtraction.
Yes. Which is what I have here, right? Times a negative,
Oh,
right? You could think about this same thing as like right? You could think about it that way also, because the -1 multiplied to the front. So that's fine, that's true, absolutely true. And you can think about it that way if it's more intuitive. Sure, rearrange it, that's okay. What do you guys think? What do you guys think? It's like, okay, Mr. Kulik. So I collected like 15 multiple choice questions from the AP site involving these 3 integration techniques. Let's do the first one together, and I'll leave the other 14 for you guys to practice. Sound good? Okay. This is a no calculator, AP multiple choice question. The pace for something like this should be 2 minutes. Try it on your own. We'll go through it here in a moment. Look at your notes if you'd like, no problem. We just did this for the first time today. You have not practiced it. 2 minutes is a dream. If you're very clever or paying close attention, you can probably do this without actually doing it, because of the multiple choice nature of the problem. Anthony shakes his head like, I see what you mean, I think. What's that?
Should have CKE.
Yeah. I thought you said D also, for the record. But yes, it is E. The answer is E. Hopefully you can just recognize that because the denominator is not factorable, the trick is going to be having to use that tan inverse as our U sub. There's only one option in the multiple choice with the tan inverse in it. So this problem that was probably like 2 minutes to do by hand on a good day, because I was clever and I knew what I was looking at, and they were nice in what they gave me as my multiple choice options, I can do without actually having to do the problem. And these are the kinds of things that, to effectively finish the AP multiple choice sections, you'll have to do, right? There will be problems where it's like, okay, I know what the answer has to look like. I'm just going to try to steal some time on this question, because I know there's going to be things that I run into that I know how to do that just are going to be like a 3 or 4 minute question. So I have to pick up some time on these easy guys, or find places where I can, do the question in 15, 20 seconds to save myself some time for a problem that, like, I'm going to need 5 minutes to kind of grind through this, because maybe it's just inconvenient. So doing this by hand, this is a completing the square problem. the work would have looked like. The goal here ideally would be, don't actually want to have to do the work if I don't have to do the work. Similarly, I think the next one you should be able to do without actually having to do anything. Which one should 2 be? Has to be A. Because I know I'm going to get like an AX plus B plus C over X minus 2. That means I'm going to have like C times the natural log of X minus 2. That's the only one that has, like plus A. Because I know what the answer has to look like. I can avoid having to actually grind through the whole thing.
You would use the division for this one.
Yes, 100%. Should be easy to recognize that because it's the only situation where the degree of the numerator is greater than or equal to the degree of the denominator, right? Okay. We did one more than I meant to. I'm going to hand you guys some optimization stuff. The first sheet I'm going to give you are just like some general notes on the optimization procedure, because it's been a minute since we've done this. I don't know if you have your first semester notes handy. This is just me kind of giving a general outline of like how to do these problems again, which I think is probably pretty useful. I would have this with me. And then we have 3 sets of optimization practices. They get like, increasing difficulty or complexity. I'm going to give you the first set today. So the first set should be relatively straightforward. The situation should be really easy to come up with an equation for or draw a picture for. The goal here would be just to refamiliarize yourself with the optimization procedure that I outlined on the first sheet that I gave you guys.
I didn't do any of them on the page. All of them on.
Okay. So for next class, try to do some of these integration technique practice. Don't feel like you have to do all of them, but this would be like the assignment for this section that we did today would be these 15 multiple choice problems. Try to do the optimization things I handed you. I think these ones, in all honesty, are quite easy once you've kind of gotten the hang of the procedure. So again, look through the other sheet while you're doing them to work on the procedure. I think that, again, this first set is mostly for you guys to get used to the steps, the actual building, like modeling the situation and like doing the calculus should be really easy for you. Our remaining, I don't know, whatever we have, like 30 minutes or so of class, we can spend doing some test 5 prep. Does that sound good? Let's just work on some multiple choice questions. Let's go with these ones. So let's do this. I'm gonna pick some of these multiple choice problems and give you guys a chance to work on them and go through them together. Sound good? Keep you guys involved. So this is a pretty decent one. So again, it's a no calculator, multiple choice question. The pace should be about 2 minutes or something like this. So again, I encourage you to have like some scratch paper, try to work through this on your own. Doesn't do a lot of good for you to watch me do this stuff at this point. Like, this is stuff we've talked about how to do. You should be trying to do this also. So find a scratch sheet of paper or spot in your notebook or on your OneNote or whatever you want to kind of scribble some stuff on. Take a look at that. And we'll go through this in a minute or so. Who sees the answer? Anthony? What's up? What is it? It's not 0. It's not 2. It's 8. So I can say that, right? Because I flipped the bounds. That guy is 3. This is what I'm given. That guy's 5. Ideally, that's a problem once you feel comfortable with it, you can do in your head. Right? Does that feel good, Anthony? Yeah. So again, the trick is you got to remember that you can hook them together. If the upper bound for one is the lower bound for the next one, and you can hook them together. That's the property we used. Let's do this. This is a similar flavor. Just with a little additional wrinkle. Who sees that? Yes, B is correct. So to just elaborate a little bit on what we did, we know 0 to 6 of F is equal to 0 to 3 of F plus 3 to 6 of F. So no, this guy is 4. And then I need 0 to 3. So when we flip the bounds, we negate. So we're going to have 1/2 4 minus 3 times 7. Everybody okay? Ooh, hard. Let's see what's another good here. Do this one. Purely conceptual. No calculation on this one. What was that? C is correct. Should have been real obvious that this is true. That's a property. If you weren't sure about that, think about it as a picture. So here's a function f. Here's a function g that's always above it. The area under g will always be bigger than the area under f. Would you agree? Because that's what an integral means. So that narrows us down to E or C, right? So we just need to check to see if either of these two properties hold, because then we know it's got to be E or C, right? Which of the two would be the easier one to check? The first derivative or second derivative? I agree. So here's my G. So I need to see if there's can I draw an F that always lives below G, but a place where its slope, because we're talking about the first derivative, is bigger than 0. Well, sure, that's easy. I could just do something like that, right? Oops. Because any spot like here or here, the slope is greater than 0. So this can't be true. Because here the slope of f is greater than the slope of g. So, can't be that one either. So this is one where just kind of drawing some pictures and thinking about what could these things look like, and seeing if the pieces hold is really helpful. Notice I drew 2 separate graphs for f and g when I was thinking about one part versus the other part, depending on what I was looking to examine. If I want to talk about slopes, I'm going to draw both the slope 0. Obviously the slopes are equal both times. I want to draw one where the slope is 0 and the other where the slope is something different. And it technically wouldn't have mattered if I would have drawn f as the zigzag and g as the straight line, right? Because here's a case where the slope is negative, the slope on g is 0. So there, f is less, or yeah, you know what I mean. It just doesn't work. Anyway, let's go on to the next one. Oh, this is a good one. Let's do that. What's that? Nope. Yes. It is B. So do that. From -1 to 0, the area under the curve is just that triangle. So I have -1/2 base times height. Again, if you're doing an area under the curve with geometry, it has to go from small to big. If you can do it as like an antiderivative and like pull the formula out, it will not matter which bound is where. But if you're calculating areas under the curve using geometry or something, have to switch the bounds so that they go small to big. Frankie, is that a question?
Yeah.
Like, get it beforehand? Okay. Keep going. This is helpful. Just kind of letting you guys think on some of the stuff and talking through things. Oh, this is a good one. I love when they give me a piecewise. Sure, yeah, of course. Yeah, how'd you do it, Anthony?
Divide mine at 2 for 2 values as an area of 4 under it. And a triangle from 3 to 5, base of 3 hash 4.
Here's the problem, though. So there's from, you know, like, this will start at 1, right? And then if I draw this part of the graph, at 3 we're at 2, and then at 5 we're at 4, right? So the area under the curve from there is into triangle. It's a trapezoid. So I agree, this area is 4. This area would be 1/2 base 1 plus base 2 times height. So base 1 is 2, or base 2 is 4, and then height is 2. So 10 is the right answer. Does that feel okay? Alternatively, what else could have you done if you didn't want to do it geometrically? I could do it all algebraically. Right? If you grind it that way, you should get the same result. Feel okay? Shouldn't matter. Oh, sure. Let's do this. So the absolute value is going to do this. So a half, 1, a half, and then a half. So it should be 5/2. And again, if you don't remember the area formula for a trapezoid, you can chunk it like that. That just happened to be, since everything was halves, we just went ahead and chunked it because it felt easier than dealing with the, than the trapezoid formula. Notice that this is a calculator problem. In the calculator section, I think it's about 3 minutes per problem is the pace. They give you a little bit more time, I think, because some problems you have to key stuff into the calculator and get stuff to come out. This is one of those. Impossible for you to do as it's currently constructed without a calculator. Notice the cuckoo crazy answers. I can't do it without a calculator. Sure. That's the fundamental theorem of calculus part 2. That I can just find from my calculator. That I know is 5. And then I can just solve for g of x. So which one is it up here? Did anybody grind through to get it? I found it 1 to 3. Oops. Ugh. X cubed is 2 dx. Now minus 5. And then I have to multiply through by the -1. So it should be that guy. Considering that you have I think 3 multiple choice questions on the calculator section, I'd expect to get a problem like this where you have to use the calculator to do it. Let's try that one. Okay, concave down means we have to look at the, the first derivative just cancels out the integral. The second derivative is this guy. I'm going to find the inflection points where we're going to change concavity from positive to negative. Luckily, this is defined everywhere, so I don't have to worry about where it doesn't exist. I'm going to divide 6 through by everything to make my life easier. So I notice that that's going to be that. So I'll make my little sign diagram, do some test values. I'm testing in the second derivative. So 1 minus 3 is negative. 1 minus 2 is negative. Negative times negative is positive. So that's concave up. 2.5 minus 3 is negative. Minus 2 is positive. Negative times positive is negative. 4 minus 3 positive. 4 minus 2 is positive. So there we go. I don't know if there's a better way of doing that without a calculator. Everybody okay there? I think we're just about out of time, so we'll stop here. For next time, if you guys would please work on those optimization questions, do a little bit of that additional integration practice. Keep studying for test 5. Don't put that off for one day. Like, build some time to where you can figure out like what you don't know how to do and what you do know how to do, and you can ask them targeted questions on Friday still. My plan is to do 6-1 on Friday and then spend some time talking about the optimization questions and doing some more review stuff. Okay, folks? Have a good weekend. Oh no. Don't do that yet. See you on Friday. Have a good day. Have a good B day.
There's no relation on the test, right?
What's that?